perceptron, and we will finish this today and perhaps start a new topic, support vector machines. So we've discussed the training error, the generalization error of the binary perceptron. Okay. And what I would like to discuss now is an algorithm for learning the way. So we didn't discuss the training and the generalization error. We discussed that for the linear perceptron, but we discussed the capacity. And actually, maybe I will remind you. I managed to start this. Okay, we have the microphone, but I think the batteries are. Never mind. So we discussed the capacity. Maybe I will remind you that the capacity of the binary perceptron, what we saw is that it is basically zero. Basically, if we look at the percentage of realizable dichotomies, which we denoted, which mechanism we use for the number of dichotomies? The capacity divided by 2 to the p. And we looked at that as a function of the dimensionality divided by n, which we called alpha. Then what we saw is that essentially as long as p is smaller than n, all the dichotomies can be realized. So this would be 1. When alpha is equal to 2, it's always exactly half. And then the dependence for other values of n, we didn't have a precise, we do have a formula for it, but we didn't, it's a sum over various terms. But if you try to evaluate it, you could do it on MATLAB. You will see that the larger n is, the sharper the transition. So, okay, we also know that it goes to 0 here. The larger n, the sharper the transition from full capacity to essentially 0 capacity. And so if we would plot, say, for 2 values of n, one of them would be kind of a moderately large n, and another one would be somewhat larger n. We see that when the n becomes larger, the transition becomes sharp. So this is large n, larger n, this is smaller n. So this is just really a reminder of what we did last time. And now, what I would like to discuss is the learning rule. So in contrast to the linear perceptron, where we had a formula for the weights that achieve, say, 0 error if we're below the threshold, if we can realize all the examples. We had a formula. We had a linear set of equations. For the binary perceptron, we don't have a set of equations that tell us what are the weights that can achieve the examples that we have. So I suppose that we're in this regime. So, but what I would like to tell you now is that there is an algorithm for learning the weights. And this is what we will do now. So we discuss now the perceptron learning algorithm. Maybe actually before I discuss the learning algorithm, I will just do another short reminder as to what is a binary perceptron. So I remind you that the architecture is the same as the linear perceptron. We sum the inputs as before, we have a set of the examples. Okay, so I will now present to you an algorithm, and the important thing that we will discuss and prove is the fact that whenever there is a set of weights that realizes that correctly classifies all the examples, the algorithm that I will write down in a moment is guaranteed to converge to the correct answer, to give the correct answer. Okay? So, but let's first write down what is the algorithm. So the first thing is you start with some initial choice of weight. Which I will call W0. You have to choose it. You can choose it as you wish. And now what we are going to do is we essentially are going to update these weights in steps, each time based on one of the examples. Okay? So each time we take one of the examples and we use it to update our weights. So I will call the weights at time t WT. And what I need to tell you is how we choose the weights at time t. So the idea is that each time we update the weights. We have a certain set of weights, and we WT, and now we see example t plus the next example t plus 1, and we want to decide what will be the weight WT plus 1. So the update here is based on the next example. And here's the rule. So the rule is going to depend on whether the current weights that we have, WT, correctly classify this example. Okay? So if if yt plus 1 times wt times xt plus 1 is equal to 1, what does that mean?
Projecting is equation is right.
Right. So write xt plus wt times xt plus 1 is the classification of the current weight of the weight wt on this vector. And if it has the same sign as yt plus 1, it means that we're correctly classifying this example. So if this is equal to 1, we're correctly classifying, and we're going to do nothing. Okay? No update. On the other hand, if we're yt plus 1 wt, I should put here a transpose here and also here. Xt plus 1 is equal to y minus 1. If we're misclassifying this example, then we're going to update the weights. And the weights are going to be, I hope that you can see this. If not, let me know. Shout and I will write it here. Okay, so the weights are going to be wt plus 1 is equal to wt plus, I will explain in a moment, eta times yt plus 1 xt plus 1. Okay? Eta is called the learning rate because it controls how, what is the size of the update that we make it each time. We'll discuss it in a moment. You can choose it as you wish. And one thing to note about this update is that it kind of makes sense because it always brings this expression, it always increases this expression. It brings it closer to what we want it to be. We want yt plus 1 times wt plus 1 xt plus 1 to be plus 1, right? So wt plus 1, if eta is small, maybe that if this minus 1, this, oh, and I should have written here sign, by the way. No one corrected me, right? I should have written here. So this is the sign. Okay, sorry for the mess. We need to put here a sign. Or, you know, the other way I could write it down is not put a sign, but just ask whether it's larger or smaller than 0. So let's do it that way. So this I'm keeping as it was. This was WT x to the t plus 1. And just put here larger than 0, and put here smaller than 0. Okay? Now, we want this thing to be plus for WT plus 1, to be positive for WT plus 1. So what I was pointing out is that this addition makes this product more positive, right? Because if you multiply this thing by yt plus 1, this is 1. You multiply this thing xt plus 1 by xt plus 1, it's always also positive. So the product of this thing with xt plus 1 times yt plus 1 is always positive, so it will increase this thing. So it's going in the right direction. Makes sense?
Again, why? I mean, the y in 6 doesn't have to be positive, false.
That's right, but yt plus 1 times 1, so let me write it down explicitly. Note that wt plus 1 times that yt plus 1 wt plus 1 transpose xt plus 1 is always larger than that in this, if we update, it's larger than yt plus 1 wt transpose xt plus 1, and this is because yt plus 1, yt plus 1 times the contribution from this addition, which is yt plus 1 xt plus 1 transpose xt plus 1.
SI is always positive, right?
Yes. Good. This thing is positive. Why is it positive? Because note that this is the norm of the vector squared, it's positive, and yt plus 1 squared is positive. Okay? So it's going in the right direction. That's what I wanted to say. But I didn't yet finish explaining the algorithm. So this is just what we do in each one of the examples. And now what we do is iterate through all the examples. Cyclically. And we stop it if there is no update in the cycle. Right? If in the full cycle there was no update, it means that we're already classifying everything correctly. We stop. Okay, so the theorem, the important theorem here, the convergence theorem, states that if there exists some set of weights W star such that y mu W star transpose x mu is larger than 0 for all mu, then the perceptron learning algorithm will stop after a finite number of steps. So it doesn't necessarily mean that the learning algorithm will converge specifically on this W star. There might be many different, actually almost always be many different choices regardless of our choice of the learning rate. Right? We can choose it as we wish. And at first thought, it seems surprising. Maybe, if we make the learning rate too large, it's a problem. Changing too fast. But I would like to point out that we should actually see that in some sense this should be the case. And the reason is that imagine that you have a set of so maybe I'll just write down no true for any eta. And I just want to think about why this makes sense that it's true for any eta. So imagine that you have a set of weights that we start with W0 and eta is equal to 1. Let's just choose eta to be equal to 1. And we run the learning algorithm and we get W0, W1, W2, and so on. And now I want to compare this with running the same learning algorithm with some other value of eta. I claim that if I start with an initial weight eta W0, then everything will be exactly the same all the time. All the weights will be the same as they were, in this case, just multiplied by eta. But the magnitude, if you multiply the weights by a constant, it doesn't matter for anything, because all we care about is the sign of W transpose times A. So if I start with this, I will end up with a set of weights which is eta W1, the same W1 is here, eta W2, eta W3. So the learning algorithm with a certain value of eta is completely equivalent in what it does to the same learning algorithm with another value of eta if we start with different initial weights. So what this tells us, it still doesn't explain why nothing depends on eta, but it just tells us that we can kind of shift the question to why is it that the initial weights don't matter. Right? So I mean, once we realize that the initial that for any set of initial weights, this algorithm will converge, it should be no surprise to us that it will work for any value of eta. And this is really because of the linearity of the binary perceptron and the linearity of every step that we do in the.
So the speed of convergence will depend on how the values of the initial condition are
Exactly.
initially distributed, because only the sign, basically
Right.
because the function is only a sign, and the sign will be determined by the linear weights.
Right.
Only the proportions of the linear weights will determine.
Well, for a given value of eta, the size of the initial weights might matter, because it kind of determines how much we weigh the initial. For example, in the first step, it will tell us how much we weight the correction relative to the first one. So it's not precisely true that that the size of your initial weights doesn't matter, but it is true that there are some other weights with the same direction, for a different eta that will give you the same convergence rate. Okay. Now, so once we realize that it's really a question of why the initial weights don't matter, I would like to pose the question: why do we need some initial weights at all? Why do we need this W0?
Because if we have zeros as the initial condition, then as long as we don't have zeros as the initial condition, everything's fine.
That's right, exactly. So we cannot start with W0 equals 0, because then the output of the binary perceptron is not defined. So we need some initial weights. Now, why is it that the initial weights don't matter? I don't have a very good answer. I mean, we will prove a theorem, but intuitively, it's because we're iterating through all the examples, and eventually, it's really the example. The initial weights are just some initial contribution, but we're adding all the time things that come from all the examples, and eventually, it's the examples themselves that matter, and not the initial weights. Okay, so
Why is it not defined as W0 as
because we need the sign, and the sign of 0 is...
Can't
What
you
does it
define
matter?
some?
Yes.
Well, that's a good question. We could have decided maybe to classify it in some particular way if it's 0, and
You do need actually somewhere to define what's going to happen with it is exactly
Yeah,
0.
because it could end up
right.
with
Although-
theoretically.
Although note that in our discussions we always kind of assume that our examples are coming from some random distribution, so the probability that
It's
it will be
0.
precisely 0 is 0. But in real life conditions, it's of course maybe a relevant set of examples that you might encounter. So we could have defined the perceptron to give some particular answer for 0, but I need to think whether that would matter or not.
But there you have y, actual sagging y, which is binary, and you have w sign of wx, which is binary as well. Like
Yes.
So multiplication, those products of both can be 0. Doesn't matter what your prior on the.
That's right. But again, we kind of assume that the probability of events like that, this will be 0.
Okay.
But it's a good point. I should think about it a bit more. But since you raised the question, remind me your name.
Alex.
Alex. Okay, I'm filling up picture.
No, we changed places.
Yes.
But your
Yes,
face
that's why.
doesn't
That's
change.
exactly. That's why.
You could change it, but it's going to take some time.
It's a different time scale from pixel.
So you're an example of someone who does not appear in the picture.
Maybe it's because I was in the back and I was not
Yeah,
able to
maybe.
see.
Okay.
Because I was definitely in the
You were there?
back. Because
Okay,
I
your name?
remember I was like, oh no, why are you taking that picture?
Your name?
Noah.
Noah. Oh, that's right. You're funny in the back and kind of small. So, okay, so now I want to prove, before I prove, another comment, another very important comment, is that if we look at this, at the update rule, one of the nice things about it is, I mean, remember, we're not doing here a course in machine learning, we're interested in the brain. So, it's kind of nice that this update rule, we can think about it. It has the type of ingredients that we would want to see in a learning rule that might occur in the brain. So, why is that true? Imagine that your brain is being shown the examples, okay, and each time your brain makes a decision, and someone tells you if you were right or wrong. And based on that, something happens in your brain. What happens in your brain? If we look at the update, what are the nice ingredients in it? So imagine that, so WT plus 1, I erased the picture of the network. Maybe I draw it here. So we have the x's, x1, xn, and these connect to our output neuron. So this would be some xi. So if we ask what is the correction to W, to the ith element of W, what does it depend on? Yes, Daniel?
So on the x's and y's, so it depends. The neurons which, the synapses which were active, that's the ones who change also.
Yes, moreover, that's right, moreover, this particular synapse, Wi, the change in Wi depends only on xi and on y here, xi and y. So, in that sense, it's a local learning rule. The change in the synapse depends on the activity of the postsynaptic neuron and the activity of the presynaptic neuron. It's a local learning rule, but it's not really a local learning rule. Why is it not just a local learning rule?
Because Y is also affected by the other.
Yes, but that's fine. Why, as long as in the update we only need to know what is the value of y, that's fine.
But you would not be only using all of it.
In what essential way are we using all of them?
Just like xt plus 1 is
No, but xt plus 1, again, the ith element of xt plus 1, if I look at this equation, it depends on xt plus 1I and depends on y. I claim that we do use the.
We have a conditional happy.
Condition, okay.
Okay, so now I need to see whether I can use this chart. Well, actually, I don't see it here. You're not here. Name.
Aviv.
Aviv, okay. Yes, so what are you going to say?
So you are using your update rule is conditional. I mean, you don't do the update if
Okay,
it's
very
not
good.
a
So,
condition about the
right, so
circumstances.
that's right. So in this if here is where we do use the activity of all the neurons, but we use it in a very particular way. We only need to know whether our choice was right or wrong, right? So if we think about the brain, where could this signal come from?
Reward.
Reward. Okay, so we can imagine that, you know, the fact that I told you, very good, you classified correctly, or I tell you, no, no, that's not good, affects the, you know, affects the concentration of some neuromodulators, such as dopamine. This is available to all the neurons in the network, and depending on the concentration of dopamine, this modulates whether they're updated or not. Now, of course, this is very simplified. This is a caricature of something that would happen in the brain, but it has the right ingredients. Yes.
That would mean if we are happy suddenly we wouldn't learn anything.
Well, in this case, if you're happy, your sinuses are not updating, and if you're unhappy, they are updating in this particular example. But we could think about other learning rules, but at least we have this ingredient that only the reward, whether you did something right or wrong, modulates whether your sinuses are updating or not. Yes.
That's pretty much what I meant, that only negative feedback.
Okay, I think you're the last on the picture, almost. No, not the last. Almost.
Ilan.
Ilan? It's I'm.
Yes.
I'm here. What? All right, so now let's prove the convergence theorem.
Can you repeat why is it a local learning rule? I mean, I use because of the transpose. I use all the input vectors and all the.
Yes, but update. So let me write it down. Update to xi. Sorry, xi. Put the index here, which is really xi t plus 1 minus xi t. Depends on
W.
y.
Yeah,
It's
the
W.
same as W. That's right.
What? Oh, sorry. Yeah. So w. Yeah, wi t plus 1 wi depends on y t plus 1. It depends on it depends on x t plus 1 I, and it depends on the reward. Now, in fact, what we would really want for a local learning rule perhaps is that it would depend on yt. But I think that this wouldn't matter much if we would replace yt plus 1 by yt. So that's actually something that we should think about it more carefully. But I think that, you know, they will be close to each other, so probably this learning rule would work well, would work okay also if we replace yt plus 1 by yt here. Actually, I need to think about it.
Why again? I'm
Well, because the sign, what matters is the, well, okay.
It's, I mean, it's
Yeah,
the
yeah,
number
yeah.
is t plus 1 and it's y.
Yeah, no, you're right. So,
It rings fine.
so it's more like, okay, but okay, so we can think about it differently. So, good. So now, I need to take back what I said that we're not necessarily updating when. So we want to let's do it. We need to do it a bit more carefully. I was a bit careless here. Let's think about it. We want it to be depend on yt.
But why?
Why? Because yt is the activity of the. Oh, no.
It's, I mean, you're an example t plus 1. You'll depend on t plus 1.
Yeah. Okay. So yt plus 1 is not the activity of the network. That's the point. Yt plus 1 is the correct answer for x t plus 1. But we can write down. So what we really wanted to show that it depends on the. It's not working. show is that it depends on xt, xt plus 1, because this is the activation of the neurons by the examples. So this is fine. And by the activity of this unit at this step. The activity of this unit at this step would be Wt transpose times xt plus 1. This is y, which is y of, yt, the y that is generated by the network based on this example. But we could write this also as the reward signal. So if imagine that we have a reward signal, which is 1 if classified correctly, and minus 1 if incorrectly. So we could write yt plus 1 xt plus 1 as Wt transpose times xt plus 1, which is what the network currently is saying based on the weight t, times yt times the reward signal. I think that this is correct. So if the network is saying the correct thing, that's the same. And if the network is saying the incorrect thing, the R flips the sign. So we could have just rewrote this update rule. Therefore, the update rule can be rewritten as, first of all, we update only if the sign of if R is negative, right? So it's a sign of minus R times, now I write this as eta times R times, so it's still, what I said before, it's still okay, but just we need to think about it a little bit differently. Yt, Wt transpose, xt plus 1. But since we have here the sign of minus R, I could also just remove this R and put here a minus. So this is minus sign of minus R, which is just the sign of R. Sorry, this is not the sign of R. This would be theta of R. Like this should be 1 if R is negative and 0 if R is negative. So I could put here now a minus times eta yt Wt transpose xt plus 1. So the whole point of all this exercise was to write it now, and it, no, I'm sorry, I'm being a bit sloppy. By yt, I mean by yt I mean the answer. So what am I doing? This is this is we have here. I want to put here R times the answer of the network at step t. The answer of the network at step t would be Wt transpose sign of Wt transpose xt.
But the word is sign, right?
The read output, so let's call the output, y tilde t plus 1 is define it as the sign of wt plus 1, wt transpose xt plus 1. Okay? And that's what we want. Okay, and so that makes more sense. So now we can write this as eta r y tilde t plus 1 xt plus 1. And so here this is just y tilde t plus 1. And I'm sorry that this was a little bit sloppy, but the point was that we can write the update as a function of the output of the network, which is like the activation of the output neuron, the activation of the input neurons, and the reward. Okay? So it's, in that sense, it's a local learning rule plus some reward signal. All right. So now what I want to do is prove the convergence theorem.
Is R one or minus one year long?
In this case, I decided to.
But eventually you're using heavy side, so.
No, but I was using it also here, not as a heavy sign. So this function is 1 if r is minus 1 and 0 if it's 1, but it's multiplied by r. So it's also like this function, which is plus 1 if r is negative.
And 0 is
Yeah.
part, so you just define
yeah,
R as
yeah.
that. Okay.
So this is just this part that if correctly classifying, it's 0, and if not correctly classifying, this part is 1. And now we have here actually if I didn't do some mistake, but you can go through it and check. The important thing is that it's the output of the network. I think that there might be a minus. No, there is a minus sign relative to here, and it all makes sense. Why? Because if we made an incorrect, actually this term exists only if we made an incorrect classification, and if we made an incorrect, so here instead of doing all this exercise, we're going to set it by word. If we did an incorrect classification, we know that yt plus 1 is minus the answer of the network. So we could have just replaced in this rule yt plus 1 by minus the answer of the network. This is a simple way to think about it.
But why is this the update? Where is WT plus 1?
Here? Or here? Or what?
Yeah.
You know what? You can do this exercise on your own and hopefully be less confused than I was, but let's just say it in words. Okay? Instead of yt plus 1 is the correct classification for xt plus 1. I want to replace it by what the output unit has generated for this example. Okay? I know that we're doing an update at all only if the network has made the incorrect choice. Right? So
Yeah,
I can replace the output of I can replace yt plus. So I know that the output of the network was minus yt plus 1. So I can replace here yt plus 1 by minus.
So just that yt plus 1 xt plus 1 is wt? Like the
No. Yt plus 1 is, we had examples, x mu, y mu. Yt plus 1 is the correct classification, for example, mu. As for the t plus 1 example. But I'm saying it's also, I know that yt plus 1, if I made a correction, yt plus 1 is minus what the network has generated in response to xt plus 1.
So just
You can, that's a nice understanding.
yeah, I'm just not finding the new WT that
The new one or the one that the network has generated?
you're trying to say this is the learning rule?
This is the update. This is just, I was writing this term.
Only this term.
Yes. Yes. But again, I think that what I said in words is clear, and this is just a sloppy formal way to try to derive it.
What is the conclusion from replacing the y plus 1 by
That the learning, we can think, the conclusion again is that we can think about this learning rule as depending on 3 quantities. the change in the synapse Wi, the update of the synapse Wi depends on three quantities. The output that the network has generated, the activity of the output neuron, Y, the activity of the output neuron in response to the example, the activity of the input neuron, the presynaptic neuron that's involved in Wi, and the reward signal. Okay, so the fact that in addition to there is a reward signal that depends on the activity of all the neurons, but other than that, the dependence is local. It depends, the change in this weight depends only on the activity of this neuron and the activity of this neuron. Okay, and these kind of rules we know that exist in the brain. We know that synapses can change their value in a way that depends on the activity of the presynaptic neuron and the postsynaptic neuron. And we also know, I mean, if we try to think about, again, how this scenario can work, that neuromodulators can modulate synaptic plasticity. So perhaps the reward signal is manifested in a slightly concentration of a neuromodulator. Okay, so finally, a proof. Oh, you have 5 minutes. Okay, I will try to do it quickly.
How much is done? I think I need some mental capacities for the proof. Or is it very easy?
It's not very easy, but on the other hand, it's not very essential. So I think what we will do is I will continue. I will ask Neta to, if we take too much time, to postpone, the start of the Tirgul. I promised it to you, so I don't want to just not to do it, but I think there is something to learn from seeing how the proof works. So the idea, first of all, in the proof is that the first thing that I'm going to do is I'm going to make some change of notation. So in principle, what I want to do is to first note that in each step of this algorithm, sometimes the weights change and sometimes they don't change. And I could, make a list for any particular set of updates. What were the times in which the weights changed? And so I just want to reorder the weights. Instead of asking what were the weights in the first step, the second step, the third step, I want to consider what were the weights in the first step, what were the weights the first time they changed, what were the weights the second time they changed. So I really want to look at WTI, the weights at the times after each change. And just in order not to drag along all this notation, I will denote this by WI. So just note that now when I say WI, I don't mean the weights after I steps of the algorithm, I mean the weights after I times that the weights have changed. Okay, so this is just notation. Now, the sketch of, what our goal is to show that the set of Ti is a finite set, right? That I goes up to some finite time, and then everything is done. And
That we have to show.
That we have to show. This is what we need to prove. And then the kind of the sketch of the proof is as follows. First of all, we know that there exist some weights such that y mu w star transpose x mu is larger than 0 for all mu. That's our assumption, that there are weights that linearly classify correctly all the examples. And what we're going to do is to look at the projection of the weights, these weights, on this particular weight. So we choose some weights that we know work, and we're going to constantly look at the projection of Wi transpose Wi on W star. But I'm going to just look at the angle between them as vectors. Don't care about the magnitude. I just want to know whether, to what extent the weights at time I are pointing in the same direction as this particular weight. So I'm going to divide here by the norm of W stars. Actually, I'm going to project my weight on this quantity. So I'm dividing by the absolute magnitude, the square root of the norm of the W star. So this is the projection of the weight on this particular direction. And what I will here I divide by WI. So it's projecting W star on this direction. Projecting W star in this direction. And one thing that we know is that this is at least this is bounded from below by the magnitude of W star. Okay, bounded from below. Or could be.
So it's bounded from above.
Bounded from above by the weight. So this is smaller than the magnitude of W star. Okay, now the sketch of the proof is that what I will show you is that this quantity has to, if I increases without bounds, then this quantity increases without bounds. But because we know that it's limited by this value, this cannot be true, so I have to stop at some finite value. Now there is one subtle point that you might say, okay, this could increase without bounds as we have more and more updates, but maybe the updates are happening more and more slowly, and somehow, we never reach a situation where we reach this bound. Why do we know that this cannot happen? That the updates will start to happen extremely,
There must be at least one update for each.
Exactly. So So because we know that we have P examples, once we pass through P, if there was no update, we're done. Right? So this is important also. And now let me show you why what I was saying is true, why this must increase without bounds if there are continuously updates. So what I want to do is to look separately at the numerator and the denominator here. So let's start with the numerator. And first I will write Wi is equal to Wi minus 1 plus eta yi xi. I know that this is true because I'm only looking at cases where there were updates, so this term exists. And therefore, if I look at, let me write this down in the if I look at Wi transpose times W star, then this is equal to Wi minus 1 transpose times W star plus eta yi xi transpose xi transpose W star. And what can we say about this thing? About this thing, yi xi transpose W star. therefore, I is at least as large as W0. Sorry, this is not WI. This is WI, the projection of, WI transpose W star is at least as large as WI minus 1 W star. And therefore, WI transpose W star is at least as large as W0 transpose W star plus I times A. At least as large as that. So this is what we can say about the numerator. That already looks nice. The numerator is guaranteed to increase in every step. But as we will see, the denominator also can increase. It just increases slowly enough that everything will be okay. So let's look at the denominator. The denominator, let's look at the square of the denominator. WI squared is equal to the square of this vector. And when we take the square of a vector, we have a similar formula as for the of a sum of two vectors. We have a similar formula as for the sum of two numbers. We'll have here WI minus 1 squared plus 2 times WI minus 1 transpose times eta yi xi plus the square of this thing, which is eta squared yi squared, the norm of xi squared. Okay, now what can we say about this quantity? We know that there was an update. It means that WI minus 1 did not classify correctly the example xi. So what does it mean about this?
Negative.
This is negative. So this means that now this quantity is, of course, it's positive. It's the norm squared of a vector, and moreover, yi square is 1. And so this quantity is at least as it's bounded from above. It's at least smaller. It's smaller than WI minus 1 square plus some b, where b, I guess, is the maximum of this overall example. So b is the maximum of eta square x mu square over all mu. Okay, so now if we put things together, let's go back to this point. We want to look at this ratio. So what we can say, actually one more step here. One more step here would be to say that therefore WI square is smaller than something, W0 transpose W star plus A times I divided by the square root of this thing. The square root of this thing is the square root of W0 square plus B times I. Okay. Right? I mean, the numerator is at least as large as something, and the denominator is at least as small as something. So we can write this down. And this one, because we have here a square root in both the numerator, and the denominator, we have a linear function of I, but here it's with a square root. So this function increases without bounds as a function of I, like eventually it's the square root of I. So it will become, if I increases without bounds, this will become large without bounds, but we know that this thing is smaller than this, so this cannot happen, and therefore we will stop. Okay? Okay. Yeah. So this thing is a function of I increases without bounds. So if I increases without bounds, at some point this ratio will become larger than this, but this cannot happen. Okay? So this is why it stops.